to an x to b, we subtract 1 from the x from it. It's now negative 4/3 plus 0. So then it's negative 2/3 x to the negative 4/3. Yes, sir?
If we get the negative, like exponents of type, do you want us to put this with the denominator? Or
Yeah, ultimately to solve, that's exactly what you want to do. Yeah, because you want to be careful here. If you don't put them on the bottom, then you run the risk of missing out on one of the potential values, so yield 0 or not. So yeah, you really want to be careful. All right. And I'll show you exactly what I mean by that right now. So under the heading of critical numbers, C dot N dot, you want to take 2x to the negative 1/3 minus 2 and set it equal to 0. Yeah, that's okay. And certainly if I add 2 to both sides, divided both sides by 2, sure, it's looking pretty good, but still, it's like, well, what do I do with x to the negative 1/3? Some would say, well, Mark, it's x to the negative 1/3. All you got to do is just apply positive or negative x to the third to both sides. That's true. You could do that. But you have to be careful. Because in this fractional exponent form, we forget the fact that this guy is sitting on the bottom. And sitting on the bottom as a cube root. I need you to be cognizant of that. So, I need to be concerned with solving that equation and all the values of x that will make that guy true. Right out of the gate, I see that this particular equation has an issue if x were equal to 0. Did you see it? If x is equal to 0, then I'm going to have a problem with that equation. But Mark, all you got to do is just multiply both sides by the cube root. Yeah, I agree. But if I multiply both sides by the cube root of x, then I'm into solving, and I'll end up getting rid of this issue that I'm clearly staring at. If I multiply both sides by the cube root of x, and I do plan to do that, I'll end up solving it, and I'll get x equals 1, and all that's great, but I see an issue before that. I see that if x were equal to 0, I would be dividing by 0, and that equation wouldn't make any sense anymore. And you see the same. So, in essence, what I found, of my critical numbers, I found a place where f prime doesn't exist. And that's at x equals 0. F prime of x doesn't exist at x equals 0. Found it. That's it. And that's how it's going to appear. You're not going to find an f prime of x that doesn't exist by solving that equation for x. You solve this equation for x, you find values for the derivative equal to 0, because that was our premise moving forward. But during the process, and it was always there, by the way, we just didn't see it until now. You look at this guy, you bypass it. And say, well, I'll just take the negative cube, both sides, get x is equal to 1. Well, I'm about to do the same thing, but when you put it on the bottom, you see that, oh, wait a minute. The domain of my derivative isn't all real numbers. It doesn't like x equals 0. So since the domain isn't all real numbers, I got to take x equals 0, whatever value is not making the domain all real numbers, and exclude it from the derivative. not differentiable at x equals 0. So we need to set this guy aside as a critical number, but for a different reason than this critical number. You can go ahead and multiply both sides by the cube root of x. So you'll get the cube root of x equals 1. Then you cube both sides. X equals 1. Two completely different critical numbers. Let's talk about the expectation. The expectation here max, min, 7. Well, because I got this from solving my first derivative equal to 0. I did not get this from solving my first derivative equal to 0. So the expectation of this guy is cusp corner vertical tangent. Now, can I go a little deeper? Because on Tuesday, I said cusp corner vertical tangent or discontinuity. Why didn't I write discontinuity here?
You already proved that it's a discontinuity.
Hmm?
You already proved that it's a discontinuity.
Would discontinuity be an inflection point? Was it removable?
Okay, so you guys are thinking more about f prime. I'm thinking about that. Ultimately, these things that we're talking about, they are about the function, not about the derivative. Max, min, subtle, that we're talking about the function. Cusp, corner, vertical tangent, we're talking about the function. Why can I conclude, proof positive, why can I conclude that the function does not have a discontinuity?
Because if you plug 0 with the original function, you just get 0.
What if you don't have the original function at your disposal? So I would agree with the point. I like the point. Point's good. And maybe my question is just a little too premature. Maybe we have to investigate a few more problems. But in essence, the answer is this. If the derivative is defined everywhere, function will be defined everywhere. Now, Mark, your derivative isn't defined everywhere. Your derivative is not defined at x equals 0. Let's investigate it further. All right, so I'm going to take x equals 0, x equals 1, and put them all on the same chart. Again, it's coming from the first derivative, just the expectations are different. And I will write discontinuity here until further notice, so we can have a deeper discussion regarding